done. Go to 71 now. 71st. Where is it? Where is it? Where is it? Okay. A pulley fixed to the ceiling of an elevator car carries a thread whose ends are attached to the loads of masses M1 and M2. Figure? Is there no figure? Okay, there's no figure. The car starts going up with an acceleration. Okay, that's like this, huh? You have a pulley over here. You got M1 and M2 mass attached to it. Okay. Car starts going up with an acceleration of W naught. Okay, cool. Assuming that the masses of the pulley and thread, as well as the masses of the pulley and the thread, as well as the friction to be negligible. Fine. Find the acceleration of the load M1 relative to the acceleration elevator shaft. And relative to the car. So first of all, the string is inextensible. We're gonna use that, so we'll need a string constraint. This guy is moving up with acceleration A. If this thing is say moving down with acceleration, I don't know. So assuming it's moving down, we don't know, with A1. Or let's not go with that. Let's say it's moving up with A1 and this is moving up with A2. Then okay, no. Let's go the other way around. This is going down with A1. This is going down with A2. It's going up with W naught. You should know that, right? So you can say okay, I'm just going to use W because the book uses it. So plus W naught is equal to 0, because these three things added up. Actually, no, not just W naught. It should be 2W naught. Sorry. So why do W naught? W naught for this thing and then for that thing. So that is the rate of, so W1 plus W naught, that will be the rate of increase of the second time derivative of the length of this string, and similarly W2 plus W naught plus second time derivative of length of this string. And because the string is inextensible, these added up should be 0. Exactly. Okay, cool. And yeah, just find what W1, W2 is and we'll be done. So what's W1? That will be G minus whatever tension is there. So T upon M1. Now because this is this pulley is massless, right? Whatever tension is over here, I think the same tension should be over here, right? Yeah, I mean like each element of this, of course, it just has to be like that, right? I mean, how could it be that? Exactly, because it has no mass, so no inertia, and that's why the tension must be equal. Moment of inertia, not okay, whatever. Plus G minus T upon M2 plus 2W naught is equal to 0. You got it. It's easy, of course. Yeah, so like this thing was W1, this thing was W2. Just remember that. Now what does it give us? It gives us 2 times of G plus W naught is equal to T times of M1 plus M2 upon M1 times M2, whatever. Okay, cool. And we need to figure out what T upon M1 will be. So T upon M1, that will be 2M2 upon M1 plus M2 times G plus W naught, right? And now just plug that in there. So G minus this thing. So, oof. Yeah, I mean like G minus this thing. That's kind of okay. Is this correct though? Looks correct. Fine, just do it. W1 is equal to G minus this tension upon M, which is this quantity. So this is going to be G into 1 minus of 2M2 upon M2. Okay, well, that stuff. This is going to be M1 minus M2 upon M1 plus M2 times G. Okay, cool. And the other stuff, which is minus 2M2 upon M1 plus M2 W naught. So that is the actual acceleration in the ground frame. Is this lagging? Whatever. So 71st, the acceleration of the load M1 relative to the elevator shaft and relative to the car. So wait, what related elevator shaft? What does that? Okay, it's the like ground frame, of course. That's probably what it means. Shaft. Yeah, that should be the thing. And because relative to the car is separate from it, so it has to be the ground frame. So let's do A. Let's do A. Uh, so shaft. With respect to shaft, what's happening is let's minimize all of this actually. So only the load M1 you want, right? So W1 that will be yeah. So we did find what W1 is. It's going to be M1 minus M2 upon M1 plus M2 times G plus minus 2M2 W naught upon M1 plus M2. That should do it. So with this shaft, this is our acceleration. Okay, cool. And now with respect to the car, that is the elevator, you have W1 is equal to, so with this elevator just have to add, actually no, not add, subtract. This thing is this downwards. Yes, so W1 is like downward right now. Exactly. So they didn't give us any sign terminology what it is. So we just say it's downward and we'll say W1. Fine. Should make sense, right? Yeah. Okay, what about W1 when you consider the shaft to be moving up by W0? So you have to add M1 W0. No, you just have to add W0. Sorry, subtract W0. Yeah, subtract W0 or add W0. It's got to be subtract, right? Because no, wait a second. If this thing is going up, right? It's going up like it's going down by negative W0. You have to subtract negative W0. That will be adding W0 basically. So this will be M1 minus M2 upon. Hey, so that's not a problem. So like 1 minus this thing is the same thing as that. So M1 plus M2 upon M1 plus M2 into G plus W0. That should do it. Okay, cool. So let's go to B now. B is the force exerted by the pulley on the ceiling of the car. So that's just 2 times of the tension. You already got what tension is, right? Yeah, so like that will just be equal to 2 times of this quantity. Where did it go? Okay, so it's supposed to be 4 M1 M2 upon M1 plus M2. Oof. This is very weird. Yeah, that should do it, I think. Okay, upon M1 plus M2 and that times G plus W0. Okay, cool. Next, 72. Find the acceleration W of the body 2 in the arrangement shown in the figure 1.15. What is 1.15? This figure. Okay. If its mass is this much times as great as the mass of bar 1. Okay, find the acceleration of the body. There's a pulley right there. Fine. Angle alpha that the inclined plane forms with the horizontal is equal to alpha. Okay, the masses of the pulleys and threads as well as friction are assumed. Oh, so friction is negligible. This is awesome. So this is just smooth, right? Are assumed to be negligible. Look into possible cases. Wait, what? Huh? Friction is assumed to be negligible, right? That makes it so much easier. So they shouldn't be that problematic. The pulleys are also massless, threads are also like ideal and everything. So cool. No big deal. Then we can just do it. Fine. So you got tension on this thing, tension on that. It's T upon 2, T upon 2. In fact, let's say that the tension in this wire is T. So this will be 2T in that direction. So you just got G minus T upon M. That's the acceleration of this guy downward. But actually, oh yeah. So if this thing goes down by X, right? Then this length of X is gone. This length of X is gone. So this should go down by 2X. Right? So this guy's acceleration, 2 times of that is the acceleration of the second block. So this acceleration is 2 times of the acceleration of the first guy, which is just T upon, so M2, M1 minus, minus what? Minus G sine alpha. So that's why I said look into possibilities, because like sine alpha changes and there's no friction. So I mean, there's no such casework exactly. It's all just in continuity. What is it talking about? Look into possible cases. I don't get it. There's only 3 cases where it's moving down, it's moving up, and where it's not moving. That's it. I don't know what these people are talking about. Okay, whatever. Just do it. So you will just have this is just the acceleration, right? Acceleration of the first guys like W1. And you want to find the acceleration of the body to, oh sorry, it is in fact W2. Sorry. Yeah, it's supposed to be W2. And this is supposed to be 2T. Yes. Now it's correct. So let's do it. Let's do it. This will be like 4T upon M1 plus T upon M2 is equal to G plus 2G sine alpha. Should make sense. We've got T into 4M2 plus M1 upon just so tedious is equal to G into 1 plus 2 sine alpha, whatever. You got the tension, just want what T upon M2, so T upon M2 will be, let's see, M1 upon 4M2 plus M1 times G times 1 plus 2 sine alpha. But the good thing is that M2 upon M1 they told us is just this eta. Is this eta or whatever this is? Just gonna call it eta. 1 upon 4 this symbol plus 1 times G into 1 plus 2 sine alpha. So this is what our tension is up. Yeah, seems like that. Doesn't it? Sorry, it's like tension upon M2, sorry. So you gotta put that in there to get the value. So G minus this thing. So G into 1 minus that, which is basically like 4 eta plus 1 upon 4 eta plus 1 minus of this quantity is minus 1 minus 2 sine of alpha. This cancels. She's got this thing. This is our W1, right? That's it. So just gonna put that in there. No problem. Ow. Ow. My eyes are hurting. Okay, this thing was our W2, right? Simplify this. It's gonna be 2 out, 2G into 2 eta minus sine alpha upon 4 eta plus 1. That should be it. Ouch. That's our W2. Now what do we do with it? So look into possible cases. I don't know what to do with that. You already said that friction is supposed to be negligible. This is it. This is our W2, the upward W2, that is. Sorry, the downward. I mean, for 2 it's downward, right? We assume it's gonna go down. So yeah. So we can think of it like that. So W2 vector, right? That will just deal with all of the cases at once. We won't have to figure out the direction. Times, so just call upper as J hat. So it's gonna be negative J hat over there. Done. Next. Okay, so now you are 73rd. In the arrangement shown in the figure 1.16, so this thing, the bodies have masses m1, m0, m1, m2. Friction is absent. The mass of the pulleys and the threads are negligible. Find the acceleration of the body m1. Once again, look into the possible. What does that even mean? Right? Friction is absent. Once again, the same thing. If there was friction, you would say look into possible cases. But if it's absent, what do you mean by that? Well, anyway, I'm thinking maybe we should go to a better thing too. So, what about T dot X method? That's something that can work, right? Yeah, sure. Okay, what was it once again? It was the work done that is zero or something like that. But yes, it had to do with acceleration and stuff. Yes, it was basically like so the tension on this guy if that's T. So T and say it's going down or let's say it is going up. No, going down is the better thing to assume. So then will be negative T times acceleration of 1 downward, then negative T times acceleration of 2 downward. Uh, yeah, plus, so over here, it's 2T right there, right? So it's 2T pulling on this thing. So 2T times acceleration of the zeroth one because both are in the same direction and that should be equal to 0. That's the thing. Now, yeah, I mean, like this just cuts all the crap in between and just gives us the whole thing. I mean, yes, it doesn't give us what accelerations are supposed to be. We still have to find them by ourselves. But hey, this is nice, I guess, right? I mean, actually, it just had to do with t into x1 minus t into x2 plus 2t into x0 is equal to 0 because the work done by tensions is 0, right? Yeah, exactly. But we can just differentiate it twice and get this form and get this relation. So, and in fact, from the next time, I won't even write this t over here. I'll just write the coefficients of t in that. That will be doing it. So it's just basically like what? It's 2a0 is equal to a1 plus a2. Where a1, a2 are the downward accelerations. So what's a0 going to be? Oh wait, isn't this once again the same thing? Because now you have to figure out things in terms of tension. Uh, yeah, it's problematic. Hmm. You know what I'm thinking? Okay, we can just get a relation directly by considering everything together as a system, right? Yeah, that's another thing that we can do. So what we can do is, okay, so the total force acting on this is, so external force, not counting the tensions in it because those are just internal, right? I mean, got, okay, no, those are not internal. There's this external force acting on this pulley and that we can't account for. So, okay, let's not do that. But it would have been so much good if we could do that. You have to do it the proper way. Fine. So let's talk about A naught. It's just going to be 2t upon well m naught. Yes, it's equal to a1. A1 is g minus t upon m1, and then this thing is just g minus t upon m2. That works, I guess. Oh yeah, like there was also something called g effective or something, but I forgot that. And really, it's not being used that much in most of the questions, so why care about it? So you got this thing. So you just have t into 4 upon m1 plus 1 upon m1 plus 1 upon m2 is equal to 2g. And why do I not remember what that was? It was like what we would do is you just got tension, right? You got tension pulling on it, and we'll just say, okay, all the accelerations, we just take them along the tension. So then it would be whatever equation we get. And then for that acceleration, what we would do is tension upon the mass minus the retarding force, the external retarding force. So for this guy, I should say the external retarding acceleration. For this guy, it would just be g. For this guy, it would be g. For this guy, it would be 0. This was on a slant, like over here it would be g sine alpha, something like that, right? You know what? Let's do it. Let's do it that way, right? So, gonna derive it. uh, so how's it going to be? First of all, you got some coefficients for the t, right? So for those, let's just say the coefficients are, I don't know, n, ni, summation of ni, ti. Okay, we don't need to do that. Summation of ni times ai is equal to 0. And then from that, you get summation of ni, and then ai would just be ni times t, where t is the tension in the string with the coefficient 1, right? That's something that we assign. Okay, minus the retarding force on this thing. So yes, minus mi times g, that upon mi. Oh, I should say g effective. So I just call this thing gi. I know, looks weird. How can g be different? It's the retarding force. It's not the gravitational acceleration, all right? But it most of the times it is gravitational acceleration that is retarding it, and that's why I'll just put gi. You could also put ai, or something else. Hey, whatever. That should be equal to 0. That makes it happen. So basically, it's just summation of ni squared times t. So just write it proper way. Summation of ni squared times t. Oh, it should be summation of ni squared upon mi. Sorry, summation of ni squared upon mi. This thing times t is equal to summation of gi. That gives us the equation directly. So just get the tension. Once you have it, we can figure out all of the accelerations. Cool, right? Okay. So let's apply this on this thing. I know, maybe it's well known, maybe it's not. I don't know. I just got this from one of my tutors, and then I forgot about this completely. But in these kinds of problems, which are repetitive, just asking about pulleys and masses falling down, maybe it's useful, right? Most of the times it's not, because the problems are not so trivial, but over here they are. So to do it fast, use this thing. So let's apply it for here, for this case. So you have t, and this thing is 2t. So for this guy, the coefficient is 2. So you just have 4 upon it's m0, I think. Okay, plus what's this going to be? For this guy, it's just 1. So 1 upon m1 plus 1 upon m2. This times t is equal to summation of gi. So this has no retarding acceleration. This has retarding acceleration. This does have retarding acceleration as well. So this is just 2g. Exactly. So you can just get the tension from that. Cool. And what are we doing exactly? Where is this 1.16? Which question was 73rd, right? So the masses have these masses. Okay, so they don't give us a relation between these masses, huh? Fine, whatever, we don't care. So you got it. Now what? Now you need to find the acceleration of the body m1. So it's just gonna be what? Your t upon m1 minus the retarding acceleration. So it's gonna be g. So t upon m1 minus g. You already got what t is. It's just a monstrous value. What is this? Are you serious? I mean, what is this? Oh God. Okay. So what we are going to look for is t upon t upon m2. Sorry, m1 minus g. And that will be G into 2 upon all of this, and that upon M2. Wow. So 4, sorry, M1, right? So for M1 upon M naught plus 1 plus M1 upon M2. And how I wish there was some symbols I could use over here. There is none. Fine. It would have been so much better if instead they talked about M naught's acceleration. Okay. This quantity minus 1. Cool. That's our acceleration. I'm just going to leave it like that. Not even bothering to do anything with it. Huh. And of course, this thing is along the string. So it's going up. So this much J hat. Okay, 74th. In the arrangement shown in the figure 1.16. Hey, wait. Oh, yeah, that's just 73rd. Sorry. 74th. In the arrangement shown in the figure 1.17. Same starting. Fine. 1.17. The mass of rod M exceeds the mass small m of this ball. The ball has an opening permitting it to slide along the thread with some friction. Right? The mass of the pulley and friction in its axle are negligible. What? And the friction in its axle. Okay, those are okay. So it's like frictionless string. That's kind of weird. At the initial moment, the ball was located opposite the lower end of the rod. When set free, both bodies begin moving with constant acceleration. Cool. Find the friction force between the ball and the thread if t seconds. Wait. Oh, okay. There is friction. Sorry. But you said that the mass of the pulley. Oh, so okay. The pulley is frictionless, but this mass small m is not. Sorry. Right. So when set free, both the bodies begin moving with constant acceleration. Find the friction force between the ball and the thread. So the friction force is pulling the thread. Okay, kind of weird. So as it's moving up, uh, right, this M is being pulled up by the friction force. Yes, and this whole string also experiences friction force downward. Oh god. But whatever force it experiences, that is like the part of tension. Isn't that right? Mm-hmm. Right. I mean, like this pulley has to be having constant tension, right? Yeah, like after M, the pulley, the string after M, you don't have to worry about that because that's not under tension. But this whole string, it is under tension, right? And the tension force is exactly equal to the friction force. Because only then can you like do the elemental analysis and say yes, the massless pieces of this string are not flying away everywhere, right? So doing that, keep on moving downward. Each of these elements, they have the same force on both sides, and then you go till M. So this element inside that bead, and as friction pulling it down, the one on top of the bead that has friction on both, the same force on both sides, so that it, yeah, that's how it should be. That's how it should be, exactly. Then just friction pulling it up. Cool. Now I understand this. So you could say that, oh no, over here what's going to happen is that there's no string constraint or anything. Oof. But can you still say that the work done by the tension is 0? No, now you can't, because it's not conservative and anything. There's just like heat and, oh god, yeah, you can't do that. Moreover, these are falling down, and then you have okay, it's not doable. Understand that it's not doable, right? Fine. So let's do it the proper way. So let's tension T on this M. For this guy, for this small m, there's tension T acting on it. It's like a friction force, of course. And This is the gravity. Over here as well as gravity. So capital mg and this got small mg, right? But the thing is that the string is not of constant length anymore. But okay, how do you figure out what friction is acting on these? That's kind of automatic thing now. Okay, so you have to find. We don't know what t is. Ah, that makes sense. If t seconds after the beginning of motion, the ball got opposite the upper end of the rod. Oh, so with respect to capital M, this ball must have been accelerating upwards. Right. Well, both of these have acceleration g downwards. Actually, no, like g minus t upon capital M, and then I was going to say it also has t upon M upwards. So, clear the idea. And now just subtract this. So it's got t upon capital M minus t upon small m, right? Yeah, that's supposed to be the, like, this is the downward acceleration, right? So when you subtract this, you are looking at the downward acceleration. It's still downward acceleration, but now this is actually upwards. The upward acceleration is t upon m minus t upon capital M. Cool. And this thing is positive. Now this is also like this acceleration, half times that, this acceleration times t squared. In t seconds this happens, so this thing times t squared is equal to this. So L basically, cool. So you can figure out what tension should be. So T into capital M minus small m upon capital M small m is equal to 2L upon T squared, and then you just get this thing, 2L capital M small m upon capital M minus small m times T squared. This is it. This is our relation that we're looking for. Everything else is just up to that point. You can erase that. Let's just write it once again. T is equal to 2 capital M small m times capital L. This is it. Okay, 74th done. 275. Oh, there's you use small l. I use small l as well. Cool. No values or anything, fine. I mean, actually, I like the questions where there's no values, because values make calculation happen, and I don't like calculation. 75th. In the arrangement shown in figure 1.18, where is it? Okay. The mass of the ball 1, where is it? Right, is this times the times as great as of rod 2. Fine. The length of the latter is this. The mass of the pulley and threads as well as the friction are negligible. The ball is set on the same level as the lower end of the rod and then released. So is this fixed to the, I think it's fixed to that. How soon will the ball be opposite the upper end of the rod? Okay, so like it will just go up, and this end and this ball will cross, and then yeah, when will that happen basically? Fine. So just using E dot x method, we can say that tension into the summation of Ni squared upon Mi, right? So let's do it. So we'll say this thing is T. Tension in that is T. So this thing will be T, and this will have 2T over there. Now both of them have retarding gravitational acceleration, right? Exactly. So Ni squared. What's Ni squared? For this guy, it's supposed to be 1. So 1 upon. So call this thing capital M. Yeah, I'm gonna use that. Okay, plus 1. Oh no, it's not 1. It's 4. 4 upon small m. This should be equal to the sum of the retarding accelerations. So it's just g plus g, 2g. Cool. And yes, tension does no force. Sorry, what am I doing? Tension does no work, right? And also there is no friction or anything, so you don't have to worry about that. So there we go. Wait, what do you want to find actually? Relative acceleration, right? Yeah. So what we actually need to find is um, so the relative upward acceleration of this thing, which is supposed to be t upon, where is it? Where is it? Where is it? Where is it? T upon small m minus g, and this minus of t upon capital M minus g, which is just t into 1 upon small m minus 1 upon capital M. That's what we need to find. Not that bad actually. So you know what t upon small m times capital M is, right? It's just equal to 2g upon m plus 4 capital M. So just plug that in here. So now this thing will just be equal to capital M minus small m times this thing. So times 2g upon capital M plus 4 small m. Oh, sorry, it should be 4 capital M and then plus small m. Sorry. Now I said it's capital M minus 1. Wait. Where was it? 1.75, right? Yeah, so the mass of the ball 1 is this much times as great as rod 2. Oh yeah, but it's like also the force is uh-huh. Oh no, this is wrong. This is just wrong. This is not what we want. Oh, this is wrong. What you actually want is 2t upon small m minus g minus t upon m, sorry, capital M minus g. That's what you need to figure out. So that will be like t times of 2 capital M minus small m, which yes, indeed it would be positive, upon capital M small m. Okay, that's what you need to figure out. And what will that be? So you know what t upon capital M small m is, right? It's just equal to that. So it's going to be 2 capital M minus small m times 2g upon small m plus 4 capital M. That should do it, right? That will be the acceleration. So you just need to figure out what that is. Fine. So you can erase that. Once you got the acceleration, what do we look for? We look for the time, right? Yeah, how soon? So this length is L. So you just have square root of 2L upon upon the time. Wait, no, what am I doing? Sorry, it's not supposed to be like that. It's supposed to be 2L upon T squared. Wait, what? No, what I was doing was correct. Sorry. We have to find T. So 2L upon acceleration, which will be this thing. Time to do it. Square root of, so 2L upon 2G, that's just L upon G. So L upon G, and then the reciprocal of this thing is just small m plus 4 capital M upon 2 capital M minus small m. Done. And yeah, since we are given that small m is just, where did it go? Eta times that. So we'll in fact just write it like eta plus 4 upon, that was it, right? Yes, eta plus 4 upon 2 minus eta. That should do it. Okay, and this will just be equal to square root of, so what's L? Where did it go? It's supposed to be what's 75th? L is 100 centimeters, like 0.1. So 0.1 upon, they don't tell us what G is. Oh, come on. Just say it's 9.8. Eta plus 4, that's 1.8 plus 4, which is 5.8 upon 2 minus eta, it's 0.2. There we go. So it's what? Square root of 1 upon 98 into 58 upon 2. Wait, are you serious? 58? Oh yeah, it is 58. Oof, it's kind of problematic. Okay. Wait. I mean, we took this into account. We took the force on 1 and 2, yes. But did we take the force because of this into... Oh no. Uh-oh. Oh, this went wrong. There will also be some returning from some force from here. What about that? Uh, Wait a second. So it has an I, yes. But its acceleration is 0 anyway, so I don't think we have to consider that to be. Right? I mean, like that just won't be there. So it's just A1 and A2 that we have to look for. So it still works out. No problem. So this is actually correct. Fine. So let's do it. Well, 15 upon 2, that is 25 and 4, 29. Uh, okay, that's square root of 29 upon 98, which is like 29 upon 2 square root of that and 1/7 of this thing. Not good. Not good at all. Fine. At least we got the value. So it's 1/7 of square root of 29 upon 2. Cool. Next question. This is 75th. So 76th now. In the arrangement shown in the figure 1.19. Okay, one second. This thing. Okay, let's zoom out now. Right, 76, right? Yes. In the arrangement shown in the figure 1.19, the mass of the body 1 is once again eta times that of grade of fine. 1 is eta times that of 2. The height h is equal to 20 centimeter. The masses of the pulleys and the threads as well as the friction are negligible. Okay, so ideal conditions. At a certain moment, body 2 is released and the arrangement set into motion. What will be the maximum height that body 2 will get up to? Okay, so this is released and then it will go up. That's what you're saying, huh? And then this is just h. Wait, what? It will just collide, right? Yeah. Oh yeah. It will just collide. It's 20 centimeters, the mass of the pulleys and threads as well as friction. So does it bounce back or I mean even if it does, it goes down and then for at one moment it was at the maximum height, right? That's it, that's all you need to know. Unless of course it actually accelerates downward. Well, that would body 1 is this times as great as body 2. The height h is equal to 20 centimeter. So this is 4 times as great. So let's say it's 4m, then 4 mg force is required. So each of these strings, I mean like yeah, tension should in that case be 2 mg to hold it like that. And if this was 2 mg, then yeah, this won't match. This won't match. It is greater force, of course. So even then it won't match, and it's gonna go down. Hey, what kind of question is this? Are you serious? I mean, it's just gonna go down, so it will go up. By how much? It's just string constraint. This goes down by h. 2h of the string is made, so that must be destroyed. So it goes 2h up. What's the big deal? I don't understand this. So it's just 40 centimeter. I seriously don't understand where is the question in this. What am I missing? Why did they give us how many times it is of body 2 or anything? It's just such a simple. I mean, like it's accelerating downwards. It's gonna fall down, right? It won't go up at any moment. then it's gonna go up, right? Yeah. Okay, so if this was, I mean, yeah, we already considered the case where this was in equilibrium. It cannot be in equilibrium because for that to happen, you would need 2 mg force over here, and it cannot be produced. At max, you can just have mg force because it's not possible, right? That's it. So it won't ever be in equilibrium or go up. It'll just fall down. That's it. Okay, so 76th was, I don't know what was. Okay, 77th. Where is it? 77th. Come on. Just zoom in. Find the acceleration of, so figure 1.2. Okay, find the acceleration of rod A and wedge B in the arrangement shown in the figure. If the ratio of the mass of wedge to that of rod equals eta. So this is to that is eta. Friction between all contact surfaces is negligible. Cool. So it's smooth and everything. Cool. First of all, wedge constraint. So think about it. It's like this. Yeah. Yeah. I'm gonna draw a better figure. I'm just gonna zoom in a bit. So this is the surface, right? Now think about it. If this guy goes down, so if this rod goes down by x, so it goes over here, then this surface must have been moved like that. So this point, where did it come from? It must have come from here, right? Because it can only, I mean, the wedge can only translate horizontally, so it must have been that point. Do you know what the angle of wedge? I mean, like it's it's obvious that this thing is supposed to be alpha, and if this is say y, this is x, then you can say y upon x is equal to tan alpha, which basically means that the velocity, or whatever, this displacement of this guy downward upon the displacement of this guy in horizontal direction rightwards, that is just tan alpha. So yeah, like do this thing, it's x, and then differentiate it twice with respect to time. So you just got acceleration of a is equal to b times acceleration of b times tan alpha. What is this? Why is this lagging and everything? Cool. So you got that at least. Okay. Perfect. Now what? So now we need to figure out where did it go? 77. Yeah, it's eta and everything. We need to figure out the acceleration of rod A and B. So their masses are given. Okay, there's the ratio of their masses are given. Fine. Just assume this thing is M, this thing is capital M. So this thing is, it receives a normal force like that, and this is angle alpha. This thing is doing 90 minus alpha, so sine of 90 minus alpha is just n cosine alpha. So n cosine alpha is the upward retarding force. There's the horizontal retarding force, you don't have to worry about that really. And then there's downward gravitation. So the acceleration, downward acceleration, will just be equal to g minus n cosine alpha upon, yeah, like that's acceleration of A upon the mass, which is small m. And then acceleration of B, that will be, so you got the same normal force acting in the opposite way, and this angle is alpha, this is supposed to be 9 plus alpha. Now we want the horizontal component because the vertical component will be destroyed anyway by the ground. So the horizontal component is just cosine of this thing, so n sine alpha, that's acting in this direction. So you can say AB is just n sine alpha. There's no other force acting on it, right? Yeah, n sine alpha upon capital M. You got it. Nice. All right, cool. And then you can just plug that in this equation. So g minus n cosine alpha upon m is equal to, so tan alpha over there. Whatever. Sin alpha by sin alpha times, well, acceleration of b is just this thing, right? Is this really supposed to be tan alpha though? I think it is actually supposed to be that, right? We did the whole thing It was y upon x is equal to tan alpha, and differentiated that. So extension of a upon x is to b has to be tan alpha. We got that thing. It must be. It just must be like that. Even though it doesn't look very correct, it has to be. The thing is, normal processes are normal, and that's the main problem. Okay, so it really is just like this. So then, got this thing over there, 1 upon m sine alpha right there. So you can say, okay, g cosine alpha minus n cosine squared alpha upon m is equal to n sine squared alpha upon capital N. So you just got n into cosine squared alpha upon small m plus sine squared alpha upon capital M is equal to g cosine alpha. Cool. It's one equation. What else do you want? Do you just want what do you want? So find the acceleration of rod A and wedge B. So you want these quantities. Okay, cool. Wow, this is going to be just really bad. Oh no. And you know what capital M and small m, the ratio between that is. So it's just eta, huh? This is horrible. Okay, that goes down, and unless you give me what alpha is, it's just going to be really hard to to write it all in this small space. You have to do it. You just have to do it anyway. So there we go. What do you want? You want n cosine alpha upon small m. That's going to be all of this messed up stuff. G cosine squared alpha upon this stuff that times m. So cosine squared alpha plus small m upon capital M. You have something from that for that, right? Body 1. Wait, no, that's 77. Mass of wedge to that of rod is eta. Oh no. So that thing would be 1 upon eta. Oh shit. Even more complication. And for this thing, it's even. What? Why? Okay. Figure out something, right? 1 upon eta times sine squared of alpha. Oh god. Really, capital M upon small m, that would be eta. So it has to be like that. So you got this thing. So G minus that. Okay. So G into this in the numerator minus that. Well, that's gone. It's 1 upon eta sine squared of alpha upon cosine squared of alpha plus 1 upon eta times sine squared of alpha. Right? So we can figure out what this thing is. It's just going to be, I hope it's correct. G sine squared alpha upon sine squared alpha plus eta cosine squared alpha. And then this thing, extension of b, we know it's just sine alpha upon cosine alpha times all this. Oh, wow. No, it's supposed to be cosine alpha upon sine alpha of this thing. So like g sine alpha cosine alpha upon sine squared alpha plus eta cosine squared alpha. This is the worst. So you got this thing. Okay. But what was our main equation? Okay, just rewind. This was our main equation, right? We're gonna color this out. I'm gonna write this down because who knows, I might need it sometime soon. And oh yeah, this is also another nice equation. So you will have acceleration of A upon acceleration of B is equal to tan alpha. So like whenever I will encounter this thing, I can just write this thing and get it done, right? Cool. And just have n into cosine squared alpha upon small m plus sine squared alpha upon capital M is equal to g cosine alpha. It's another important thing to remember. Then finally you have this. So yeah, extension of A. Actually, no, you know what? This is not that important. It's just an intermediate step. It's not a result. So extension of A is this quantity G times sine squared alpha upon sine squared alpha plus beta cosine squared alpha. And extension of P, that will be G sine alpha cosine alpha upon sine squared alpha plus eta cosine squared alpha. Cool. Next. 77 done, 78. In the arrangement shown in the figure, what? How much charging? Yeah, quite a lot of charging. Okay, this has no charging. 37%. Fine, we can go 2 more questions, right? Let's do it. So 78. In the arrangement shown in figure 1.21, the masses of the wedge capital M and the body small m are known. The appreciable friction exists only between the wedge and the body small m. Friction coefficient being equal to k. The masses of the pulley and the thread are negligible. Find the acceleration of the body small m relative to the horizontal surface on which the wedge slides. Okay. Wait a second, but that would be in both. Uh-oh. Yeah, I mean, like, that's in vertical as well as horizontal direction. So how am I supposed to? This is just horrible. Okay, okay, think about it. There's that normal force acting on it. Yeah. Uh, Fine. First of all, what's the downward acceleration of M? That's just going to be G minus of whatever tension is there. Right? So throughout the string, whatever tension is there, P upon small m, right? That's equal to, so this acceleration, if it goes down by whatever amount, say x, then like there's x bit of string, new string made, so this x amount of string should be consumed. That's why m will move towards x, so m will move towards right by x. So that means downward acceleration of small m and rightward acceleration of capital M are equal. What's the rightward acceleration of capital M? Well, you got tension pulling it up, tension pulling it down, that cancels. You just got tension pulling it towards right, and then like tension pulling it down. That also happens. Like it's just tension over here. And then this complete body is like T upon capital M plus small m. You don't believe me? Seriously, you can just have normal forces. It's like normal force upon capital M. It's like T minus capital N upon capital M. Just write this down. Right? That would be this acceleration. But then this acceleration is the same thing as the horizontal acceleration of small m, which is just this thing. And then by theorem on equal ratios, we can write this thing as T upon capital M plus small m. So there we go. Cool. And in fact, yeah, this is a nice thing that the horizontal acceleration is also the same, huh? Weird. Anyway, now time to solve this. Figure out what tension is, and yeah, it can't be that hard, can it be? Oh, there's also like friction. Uh-oh. Uh-oh. Fine, the horizontal thing still works out, no problem with that, but the vertical thing is not G anymore, and not minus T upon M. There's also the friction. Oh god. So let's say that the friction is acting downwards. So this will be, so frictional acceleration, that's small f minus T upon this is equal to, like this frictional acceleration is dependent on the normal force. Oh no. Which will be this acceleration times small m. So this is dependent on this acceleration itself, right? So you can see like mod of this thing, it's less than or equal to whatever coefficient friction is times T upon capital M plus small m. If it is moving, then this friction would be this. This is just awful. How do we know if it's going down or what? Okay, can it be that this thing starts moving up by itself? No, like why would friction make it happen? And there's also just no force that is pulling capital M to the right, right? That shouldn't happen. So it has to go down. Then in that case, you can say if it is going down, then friction is positive and it's equal to k times of this acceleration, right? So plus k times of capital T upon capital M plus small m times, okay, all that stuff, capital T upon this thing. This is equal to the acceleration that we are looking for. Oh, not this, sorry. Not this equation because this equation is flawed as we saw earlier. Okay, let's do it. So G is equal to T upon small m, it's capital M, times 1 minus k plus capital T upon small m. This is so complicated. Now what? What we're looking for is basically capital T upon, sorry, capital M plus small m, right? Hey, why don't we directly why don't we use that directly? It's like A times 1 minus K. And then this thing, instead of writing like that, we just write it as capital M plus small m upon small m times K. Perfect. You can just find what the acceleration is supposed to be. Done. So it's equal to G. So A is equal to G upon all of this messed up stuff. You know what? We'll just say capital M upon small m is eta. So this will be 1 plus eta, which is G upon 2 plus eta minus K. And I'm amazed it didn't cancel itself. Yeah, it did not cancel itself. Wow. Amazing. Oh, yeah, it should cancel itself. Okay, it's going down, right? So the friction is pushing up. Oof. Then this should be negative as expected. Wait, no, it still doesn't cancel because it's just 1 plus K in that case. Fine. So now it's like this, huh? No big deal, it's still the same thing actually. Okay, and it's still capital T upon capital M upon plus small m that we are looking for. Alright. Okay, time to go. So now we got the acceleration. We want to find the actual magnitude of the acceleration of this small m. This x component and y component of the acceleration are the same. So just square root 2 times this. That should do it. So it's going to be g square root 2 upon 2 plus eta plus k, where eta is equal to capital M upon small m. That should do it. Cool. Okay. 79th. Yeah, they took a hot surface. That's why I took the ground frame acceleration. Yeah, that's correct. Okay, 79th. What is the minimum acceleration with which bar A, figure 1.22, bar A should be shifted horizontally to keep bodies 1 and 2 stationary? Oh, so if it just stays, right, it's just like that, then body 2 will pull down 1. Yeah. So there's coefficient of friction between bar and the bodies. Okay, that's equal to K. The masses of the pulley and the threads are negligible. The friction is, the pulley is absent. Another long equation. Oh, come on. So the thing is, its normal force is changing. There's gravity acting on it, yes. Pseudo forces, maybe that's the way to do it, you know. So you can just have a force acting on these things. Like normal force should just be, yeah, exactly. And then there's like friction. What is this? Okay, so 1.22. This figure What was this question? 79. Let's do it. And what's our aim? Minimum acceleration, so that it's these are in equilibrium. Fine. Okay, showing the pulley is absent. Let's do it. Okay, what do we? Okay, so this is on, huh? Right. Nice. So with respect to A, what's happening is that one is, so if it's going with acceleration A towards right, then this has a pseudo force. So M1A, pseudo force like this thing, there's this tension pushing it this direction. There might be friction, but we don't know. Wait, we want minimum. Okay. So there will be two such critical values that we have to look for, a minimum and a maximum. So if I keep on accelerating it too much, what will happen is that it will start going back. Right, and we just want the minimum value. So when it's minimum, it's actually going to go forward, right? It has tendency to go forward, but our MA is it's just big to stop that, right? So when it has tendency to go forward, if there was no MA, it would have tendency to go forward. The friction would be acting down, backward, right? In this case as well, the friction should act backward because it's just near to that. So this is friction acting in this direction, and because it's critical condition, okay, we'll figure that out later. F1, I mean, which of these is the critical conditions? That's what we have to figure out. We got this pulley, everything. Now there's tension pushing it up. There's M2 and gravity M2G pushing it down. There's also friction pushing it, I think, up. Okay, this might be that F is in this direction. Okay, we don't know, huh? No, it has to be in this direction because, wait, how can we say that for sure? I don't know. Okay, anyway, that should be in this direction, probably. Okay, let's figure out when will this accelerate downward, right? Yeah, we can figure that out, right? When will this accelerate downward, and at what particular point will the acceleration become zero? Because it has to be continuous. The graph of this A guy's acceleration versus the vertical acceleration of 2, right? That has to be a continuous graph because physics, come on. Then of course you can just go the other way around. That will start at the condition where these are accelerating downwards, which will make F1 and F2 be trivially this direction, known magnitudes and everything. And from there we'll go to the critical condition. Yeah, that should do it. So F1, this will just be equal to, okay, bad habit. I mean, actually it's a good habit to write mu because everyone uses mu, but this book, it uses K. Who does that? Okay, K times of mg, m1g, sorry. Yeah, because that's the normal force. So yes, but for this guy that's not the normal force because now it is having acceleration in this direction. So the normal force will be m2a, and that's why this is going to be K times m2a. Wait, so do these K differs? It's like K1, K2 something. You know what? I'm gonna use K1 and K2 because I just want it to be done once and for all. Okay, and this M2G, pulling it down, right? Cool. Now, what do we do with it? Of course, equate accelerations. So just have G minus, oh, this was that thing. So G minus T upon M2 minus K2A, right, is equal to yeah, this things like this is T upon M1 minus A, right? That only makes sense. Okay, and this has to be equal to 0 for it to slide down. When it's equal to 0, that's a critical condition. So when it's equal to 0, just have G minus K2A is equal to actually m2 times that. That's equal to tension force, and it's also the tension force is also just m1a. So there we go. You got what a should be. Hey, this was actually very easy. m2g is equal to, oh, why is this not friction? I didn't take that into account over here. Sorry. Minus a and minus, so friction pushing it back, divide by m1, so it's gonna be what, k1g, cool, that's equal to 0. So this is not correct, it's slightly different. So from here the tension will be m1 times all this mess, right? From here tension was m2 times g minus k2a. Here it will be m1 times a plus k1g. Okay, yeah, now we can find what a critical is. It's got a times of m1, wait, what, isn't this supposed to, okay, yeah, I mean, like, it's just, this is not a force, of course. There we go. So m1 plus k2 m2 is equal to g times of m2 minus k1 m1. Makes sense. So a is equal to, done. Oh, it should be like, yeah, it is m1, sorry, it's correct. Start differently. Cool. This is it, 79th, done. This is when it will be in equilibrium. Cool. Regardless of what these friction coefficients are, this will be the minimum value when they're in equilibrium. There will also be a maximum value. Like this is just a min. Photo 80, last question. Prism 1 with bar 2 of mass m. Where is it? Figure 1.23. Okay. Prism 1 with bar 2 of mass m. Place on it, gets a horizontal acceleration w directed to the left. Okay. At what maximum value of this acceleration will the bar be still stationary related to the prism? Oh, okay. If the coefficient of friction between them is fine. So just go for the reference frame of this prism. So pseudo force acting on it. Yeah, right. And then we'll just take this surface to our base. So there's this acceleration on this guy is just g sine alpha. There's the pseudo force acting on it, which gives an acceleration of so this is moving with what, a, right? Oh, this should be like this. Yeah, which is also alpha because look, this line will be parallel to that, so this will be alpha as well. So this is going to be alpha, and yeah, don't do this. And it's going to be a w. Sorry, they use w everywhere, right? Wait, what 80, right? What maximum value of the acceleration bar is still stationary related to the prism? So friction between this k less than cot alpha, whatever. So friction is opposing this probably. The the acceleration that's pushing it in, that's just g cosine alpha, and then it's like normal force and everything. You got mg cosine alpha as a force that times coefficient of friction, and that about m basically. So this is gonna be what, kg cosine alpha acceleration in this direction. So do the thing. This g sine alpha plus w cosine alpha is equal to kg cosine alpha. I really don't like k. I like kg. Looks like a unit. And then there's this thing, which, okay. The thing is, the normal force is not this. Okay, I get it. There's w sine alpha over there as well. So this is not correct. Instead, it should be k times of g cosine alpha minus w sine alpha. That will be correct. This is it. Just one equation. You don't have to worry about anything else. And of course, this thing g cosine alpha minus w sine alpha, it should be positive. Yes. Yeah. So there we go. What was I doing once again? Sorry. G sine alpha plus 2 cosine alpha is equal to this friction. So k times of g cosine alpha minus w sine alpha. Now we need to find what w is. So w times of cosine alpha plus k sine alpha is equal to g times of k cosine alpha minus sine alpha. This is the maximum w. So for the critical value, this should be the thing. Just divide by cosine alpha, so it's like k minus of tan alpha, a better way, tan alpha upon whatever that's like 1 plus k tan alpha. Looks very similar, doesn't it? If say k was tan of beta, then this would just be tan of beta minus alpha. But yeah, they didn't give that kind of relation. We could do it, of course, but hey, whatever. They're saying k is less than cot alpha. Why would we what's the big deal about it? I don't understand this. Yeah, fine, k is less than cot alpha. Then what? How does this make any difference? Oh, okay. Now I understand what they're doing. Oh yeah. Yeah. Wait, but isn't this like tan alpha should be better than k because g cosine times k, that is bigger than or equal to g sine, and that would just give us k bigger than or equal to tan alpha for it to be at like yes, basically. Wait, are you seriously saying like this? So this quantity will be, oh no. Do we have to use this restriction? I think we have to. If we use this restriction, we'll get a tighter inequality probably. Okay, first of all, let's check if this is correct or not. That has to be alpha, like the W acting on this is supposed to be alpha, yes. Yeah, that has to be alpha for sure. This is W cosine alpha in that direction. First of all, what you have is that G cosine alpha minus W sine alpha should be positive. That just tells us that cot alpha is bigger than W upon G. So W is less than G cot alpha. That's one thing for sure. Uh, how does this even help us? It doesn't. It just doesn't. Is this quantity less than is this quantity less than G cot alpha? You're saying that it's like, so you're saying this thing is always less than this. That was the same thing as saying k tan alpha minus tan square alpha is less than 1 plus k tan alpha. I mean alpha is acute, so and k is a positive, so this is correct. And that would be the same thing as saying wait, what? Oh, this gets cancelled. Awesome. So negative tan square alpha less than 1, obvious. I mean negative is less than positive. Okay, this is cool and all. How do we use the fact that k is less than cot alpha? So that would be like 1 upon k. No, I don't want to use 1 upon k over there. You could think of it like, I don't know, g. Okay, what would happen if I did use 1 upon k right there? Ooh, that could be some weird things happening right there. Huh. So you could write this as, no, don't think of it like that. It would be like, okay, 1 upon k is bigger than tan alpha. That's what we are saying. I understand that. Or you could say k is less than 1 upon tan alpha. How does this even make sense? Why would we want to do something like that? This is tan inverse of k minus alpha. Right. Now, K is positive, so tan inverse of K is an acute angle, and of course W has to be positive as well, right? I mean, we already got it. We already got the fact that it was happening, right? Well, K has to be bigger than tan alpha anyway, right? Oh, okay, wait. K has to be bigger than tan alpha and huh, maximum acceleration. It's less than or equal to something. That's what we have to do. But I don't get it. Where can we use that fact? You can't just put cot alpha in there, can you? Or maybe you can. Who knows? So K is positive. Tan inverse of K is in the first quadrant. Uh, Tan is an increasing function in the first quadrant. So as tan inverse of K increases, this complete thing also increases because tan inverse of K minus alpha is the first quadrant. Obviously, this thing is sorry. This argument is in fact not the first one. It's in negative pi by 2 to pi by 2, and it's still increasing. In that region, tan is increasing. So yes, put K as the maximum quantity, which would be cot alpha, and you will get what maximum W should be. So when you put it as cot alpha, it just becomes tan inverse of tan of pi by 2 minus pi by 2 minus alpha. So this will just be equal to pi by 2 minus 2 alpha, tan of that thing, which would be cot of 2 alpha. So the maximum would in that case be cot of 2 alpha. How does that even make sense? No, something must be really wrong about this, right? It has to be that there must be something wrong. It's like k cosine alpha minus sine alpha. Cool. Everything is going correctly, but I don't think that's what they want. If this was like tan of, I don't know, something that gives us the nice value like pi upon 4, I would have accepted this thing. But this being 2 alpha, a cot of 2 alpha, fine, I'll just write it down. Okay, no big deal. This is what W is. So W critical, so like maximum or whatever, is equal to G tan inverse of K maximum minus alpha, which is just G cot of 2 alpha. Cool. This is it. Not going any further than that. So it is done. See you in the next video. Bye.